Hi everyone, this is a video for the Math 6 series at UC Riverside. What I want to try to do today is explain where this common equation comes from. So a super common error early on in math is when you have the sum of two numbers and you square it, to forget this plus 2xy in the middle here. It's very easy to think that x plus y squared should be equal to x squared plus y squared. So I want to try to explain where the plus 2xy comes from, and also to try to give a sort of memory trick for how you can remember this formula and what I guess you could call higher dimensional versions of it. So x plus y cubed, x plus y to the fourth power to the fifth, and so on. This memory trick itself isn't something you need to know or will be tested on. It's just my advice for the easiest way to remember how to do all this and why it works in the first place. You can always just memorize it, but I find it easier in the long run to try to get your head around why the formula is what it is. Okay, so well, where does it come from? The formula here comes from the distributive law, which, that usually doesn't give anyone too much trouble. The distributive law just says that if you have one number being multiplied by a sum, you can distribute the first number across the sum to both numbers. In other words, 3 times 9 plus 2 is the same thing as 3 times 9 plus 3 times 2. You can use that law to work out what this here thing should be. So if you want to be hyper detailed, what you would do here is you would first write x plus y squared as x plus y times itself, because that's just what squared means. And then you can treat this as your first number in this distributive equation here. I've tried to color code what's going on. And then your x and y in the second set of, in your second sum set of parentheses, will correspond to the second and third number in this distributive law. So in that case, what you can do is, again, distribute the first number across the sum of the second two numbers. And then once you have that, you have, again, something that looks quite a bit like this expression over here. And so what we're going to do here is we're applying the distributive law twice. Once here, and a second time here. And so between these two lines, all I've done is I've written the exact same expression, but I've just recolored it to kind of show where we're applying the distributive law. And then sure enough, now instead we're thinking of x here as our first number. It's written on the right, but we're still thinking of it as the first number in this expression here. Just because, 2 times 7, same thing as 7 times 2, order of multiplication doesn't really matter. And then again, we distribute the x across this sum, and then we can distribute this y across this sum. And so what do we get? Well, if you don't reorder anything as you go, you get x times x plus y times x plus x times y plus y times y. And then when you, consolidate everything and sort it out, what you're left with is 1x squared, 1y squared, and 2xy's. So that's where the formula comes from and how you could derive it with the distributive law. Sometimes this formula is called the freshman's dream because it's common for freshmen to forget the middle part. But it turns out the same formula without the middle part actually does come up later on in more advanced math. But we don't need to worry about that today. So what did I want to show? I wanted to show the analogous expressions for larger exponents. So for instance, let's just say we want to calculate x plus y cubed. Well, what we can do then is, we could start from scratch, but that would be even more tedious than this is. So what we can do instead is just remember what we did over here and start by breaking up the x plus y cubed into one x plus y squared and then another x plus y. Because again, x plus y cubed just means x plus y times itself 3 times. Then we can substitute what we got in for x plus y squared at this step. And now I've color-coded it hintingly again. Same thing. We have one number that we can distribute across the sum of two other numbers. I'm calling these are variables, x and y, but I'm calling them numbers just because if you're ever very confused, it sometimes helps to remember that variables just represent a number that you don't know what value it is. And so, okay, what do we do next? Well, okay, I'm going to skip steps here, but we distribute the x to this expression. And so the exponent on top of each x will go up by 1. In other words, the x squared will become an x cubed, the 2xy becomes a 2x squared y, and the y squared, which doesn't have an x, gets an x, so it becomes xy squared. Then we do the same thing with distributing the y to the second line here. So this first line represents distributing the y to this number, or sorry, the x to this number here. And then our second line represents distributing the y to this expression. And then what I've tried to do is line them up so that we have like sums vertically. So we have a 2x squared y from the first expression and an x squared y from the second expression. We don't have any y cubed from the first expression, we have a y cubed from the second, so on and so forth. You can add these up vertically, and then what you get is this expression. So maybe you've seen this, maybe you've memorized it, maybe not. But sure enough, this is the expression for x plus y cubed, where you have your coefficients, and remember there's always an invisible 1 in front of your coefficients here, would be 1, 3, 3, 1. And so maybe some of you that remember Pascal's triangle might be suspicious at this point. So Pascal's triangle is just a triangle of numbers. You start with a 1, and then every other number in the triangle is just the sum of the numbers above it. So for example, 6 is 3 plus 3, 5 is 4 plus 1, so on and so forth. You can go on forever as long as you like. And it might seem suspicious that here we had 1, 2, 1. In Pascal's triangle, we have a 1, 2, 1. Then for x plus y cubed, we have, again, 1, 3, 3, 1. And in Pascal's triangle, we have 1, 3, 3, 1. In fact, you could even interpret this original x plus y as a 1 in front of the x and a 1 in front of the y, matching up with the second row of Pascal's triangle. I guess if you wanted to go backwards even further, so you would have x plus y squared. You could go back again, x plus y to the 0. And assuming x plus y itself isn't 0, this is just going to be equal to 1. So you can interpret that as this top one in Pascal's triangle. Anyways, why is this happening? Well, you can see what happened here is we took the previous expression that we got for x plus y squared, and then we shifted it over and then added up all the coefficients, the numbers in front of our variables here. And so if you wanted to calculate, say, x plus y to the fourth, you could very tediously apply the distributive law, what would it be, like, I don't know, 7 times, something like that, to work out extremely precisely at what a mathematician would say the axiomatic level what x plus y to the fourth is. Or instead, you could think the same way as we did here, where you just take this expression, you drop it, shift it over 1, and then add everything up. The effect that this has is that each coefficient in your new expression will be the sum of the 2 coefficients above it in the previous expression, if you line everything up correctly. So this is kind of why these expressions match up with Pascal's triangles, because this sum of the 2 numbers above it pattern appears over here with powers of sums as well. All right, well, that's my memory trick and explanation for where this formula comes from.